Bene.
Okay, so well, welcome here, everybody. It's not a huge match, but we're also recording, so I think that most of the people that is interested in this topic and are in complexity, 72 hours, they later will see the talk. Okay, so it's a pleasure to introduce Armando Bazzani, that is a professor in the University of Bologna. And actually, the first time that I heard something about you was the work that you did with the cars and the trajectories of the cars. But later, there has been more overlap in, like, for instance, we have here Riccardo Galotti working at IFISC, and he was one of your PhD students. So it's very nice to have you here, and welcome, and the floor is yours.
Thank you very much. So thanks to Jose to give me the opportunity to visit IFISC. That is my first time here. Today I will give an overview talk, about what is the activity of Laboratory of City Science, great name in the Department of Physics Department of University of Bologna. And I will underline physics because we are physics, and my point of view is the point of view of physicists. So the title is about digital twin for a city. And I will focus on the problem of sustainable mobility and between data and predictive models. So why digital twin? There is a project in Bologna, but I think in many cities now in Europe, with the idea to build this system that we call digital twin for a city, for just try to solve all the complex problems that the city present, and one of these problems is about sustainable mobility. That is probably the first problem we will cope with. So just a few words. How to move this? Okay. So what is a digital twin? And the answer I don't know. So it's something that, in some sense, I will use this phrase about così fan tutte. Digital twin is something that everybody say that it exists, but nobody say where is digital twin. But this is just a picture you find in internet and say, okay, digital twin is a copy of a city where you can simulate all the subsystem of the city in order to get a result. And the idea is we want to monitor all the cities. So we want to to build a system which is able to collect all available data from many systems, from satellite, from spread sensor in the city, and any data also from internet. We want to use this data to show how the city and all the subsystems of the cities are working. Then we want to predict possible future evolution for the city, and what is important, we want to simulate new scenario in order to find best solution for the problem. Of course, this is a dream. In some sense, if we are not able to understand the city, it could be difficult that we are able to understand such a complex system. Even if we have a powerful of HCC simulator and maybe a lot of modems. And on my point of view, okay, you have just an idea that you can build a pyramid with a lot of layer in which you take data and insert the knowledge we have, and for complex system city, we are interested just in the last part because we are interested in modeling, we are interested in prediction, and to build finally a simulator. I will stress that I believe that the only possibility is not to build a digital twin for beginning with all the city inside. My vision is that the digital twin is something that we will build from a vertical problem, for example, sustainable mobility. So we built a digital twin for the sustainable mobility, just focusing on that. And in some sense, I believe still that the reductionist approach of physics and the idea to relate what we observe to some primary causes is something that in order to have a good predictability of our system is fundamental. So what are the problems about the sustainable mobility? The first problem is to reduce the congestion impact, the mobility cost. The mobility cost means also, in some sense, time cost of mobility. So if there is congestion, you are losing time in congestion, and cost means also just the money that you have to invest in order to satisfy your mobility demand, which is in some sense a demand of freedom. Everybody wants to move. We want to improve the soft mobility, the use of bike, car sharing, public means. And so we have to find system able to understand how people are using the soft mobility, or why we are not using the soft mobility, where we use private car, and also which are some behavior that can improve the use of soft mobility. Then, of course, we have a reduce of environmental impact, and I want to have a global approach. So it is not, for example, sometimes a good idea. Okay, we close our historical center in Italy, and all the traffic is around the historical center. What they did in Milano. That means that a lot of traffic is just going around Milano, and the people living there has a decrease of life quality. So the life quality has to increase in a democratic way, not only for rich people. So this is the main problem that we have to cope with. And the approach is based on two things. Big data. Big data is what you can extract from internet, and this is a usual work we did in last year, but also big data is, for example, the data for information communication technologies like mobile phones, so data that you can extract in an active or passive way, depends, using people that with a mobile phone leave a GPS trace of your mobility. And then we have also our possibility, for example, in Italy, they have a black box in the car that are recording just the movement of the car for insurance reason, and this data could be available. Sometimes you have to pay, but it could be available to study mobility. All these sorts of data now are in the market and can be used to study mobility in a whole city. But of course, you have to extract the right information. And to extract the right information for big data is still an open problem. It's not clear when you have this big data that are in any case a sampling of all the possible data, because you can have everything. How you can create algorithm which extract an objective and information that can be tested in some experiment. And then you have models. About models, okay, now we have been a bifurcation in models. There are the classical models in which you simulate, you use a dynamical system, essentially you could create some evolution of your system, and there are models based on, say, neural network, artificial intelligence, deep learning, what you want. And this bifurcation has the meaning that, okay, if really you have a data set where all the possible scenario has been observed, then probably deep learning and artificial intelligence approach is quite good. If instead you have only a partial observation, then the use of dynamical system, which is a simplification of reality, is still a good solution, especially when you want to predict something that has not observed. And for me, this is something that is a key point, because, okay, you have a phenomena of black swans. In some sense, we want also to be able to predict the black swan. Otherwise, we, for example, you know, in the last news in Emilia-Romagna, which is the region where I live, you can have this extreme phenomena that is a disaster if you are not prepared to black swans. And this is still a problem where a classical dynamical system model can play a role. So I will talk now about congestion. So what is the classical approach to congestion? So this is data from a magnetic coil. Is not an urban road, it's an extra-urban road, and we have this data from a system which is installed in the Romania region. And this is typically a fundamental diagram where you observe that a lot of data are in a free flow situation, but sometimes the system will decrease the velocity with respect to the density, and then you have this fast decrease of velocity, and you have the effect of congestion velocity. So this is a phenomenon which is related to the interaction of vehicle along the road, which create a congestion as a drop down of the flow in the velocity. So, for example, in order to understand and predict this system, we really need the data of any vehicle. So we really need following the vehicle in the road and to understand when congestion is formed. And of course, the answer is no, because there are a very simple model that is related to the optimal velocity model, where you have a time delay. Simply that your vehicle is just adjusting the velocity with some delay with respect to the distance with the front vehicle. And if you take any model, it is just necessary that the optimal velocity is a decreasing function with the distance. Then you get a critical relation with the delay time, and you have a soliton that is formed by this system. You should take periodic condition, and this is the congestion stop and go. So you have not to have any data, but just some information about this in order to understand that you have a critical density, and then over this critical density, congestion appears. And this is something that is interesting, because you are relating in a very simple model the complexity of congestion formation. Of course, you want also to be able to predict. So, for example, what you can do to predict this system. Any system in physics which tends to some critical points, usually if you look to the fluctuation, you find some anomalous behavior. So the idea is that you just take this system, this is the flow of the system, you can just try to understand the susceptibility of a system to fluctuation, and then you get some analytic formula that say, okay, when you increase the density, you find that the fluctuation should increase because the stability of the system decrease. And then what you observe from the data is the following. For example, here is the same data, but just in time. And so here you observe that the flow, that is the black row, increase when you get the maximal value, when you drop down of the flow, that is typically when a stop and go appears. But if you look to the fluctuation, this is renormalized in order to have the same scale, then you see that the fluctuation, instead of increasing just in the idea of this equation, the fluctuation will decrease before that the stop and go appears. Why this? Because when the traffic becomes dense, the people is not using optimal velocity model. Because if you are too near to the next vehicle, you just say, okay, car following. I just take my velocity to the same velocity I have in front of me, and I don't care about the distance. I will not be just back. And this is a change of behavior. And for example, this can be used to understand when the system start to arrive to a critical condition. And then you can start to alarm or to give some, say, automatic vehicle the order to keep a constant velocity in order to reduce the probability to get this. So this is something that is possible, and in the if it's possible to collect the data in real time, then we can have this alert. Then just a word about what is predictability, because sometimes predictability is used not in the correct dynamical system meaning. So, for example, if you have a die and you throw a die, then you can say predictability of 1 is 1/6. But this is not predictability. This is just the probability of a stationary distribution. So if you, for example, compute the entropy, information entropy related to the stationary distribution when you toss a die, then the predictability can be defined as exponential minus the information entropy. And if this is the information entropy of a stationary state, you can say that the system is unpredictable, because any knowledge of past state give no knowledge of future. So it's useless to make any study of what are the sequence of a die, because you know that it's impossible to predict. And if you go back to the dynamical systems say, okay, you can relate the predictability to the entropy production, which is related to the positive Lyapunov exponent, the minus sign. And if you have a system which has a large positive Lyapunov exponent, then it means that it's not predictable at a certain time. It's not possible. So any system, any artificial intelligence you can use is just as to go to somebody which open a chicken and look to inside and try to predict something. So in some sense, to understand the predictability of a city mobility is still a problem that we have to cope with, because it's not clear if, for example, it's not predictability to say, I don't know if you know about Bologna, but in Bologna, everybody who lives in Bologna knows that there are areas in Bologna that at 8 o'clock in the morning is better not to pass. But Federico knows perfectly this, because you use the car every day. And so to make a prediction that tomorrow I will find the traffic jam there is not a prediction. It's just the fact that the system is periodic and we have the same traffic load all the day. So prediction means to predict the variability of the system. And in fact, the Lyapunov exponent is to relate to the fact that I change a bit the system at this time, and I know also the past history. I want to predict what happened in the future. So we have to be back to this. Then this is, in some sense, my receipt for a digital twin for city mobility. So study the data, try to create also a hierarchy between the data in order to make different source of data together and order the data according to the information you have. Define a meta model. What is a meta model? A model which can be related to our model with different time scale in order to understand, for example, the mobility at a scale of a city, of a scale of a block, or a scale of a single road. And then predictability means you have to validate the model to really with some between common physical experiment in order to see if, for example, in presence of some new events, like a big show or something, you can predict what happened in the city for the mobility. Then, of course, this is just a simple example. Everybody can build a model. This is San Francisco, but this is just a model we just built in order to understand, simulated the single vehicle dynamics. What is the evolution of a system? Here, okay, this is our resource, so you create some queue in the source, but we are increasing the load here, and then you have a grid, and then you have rules in the grid, and okay, you can create and see how the congestion appears in your system, and then also maybe how the congestion spreads. But I want, in some sense, more. I want to understand which are the phenomena of congestion rising in a city where you have cross and a lot of rules and so on. And I think this is something even too microscopic to understand this. So the idea is, okay, in order to understand, we start again from the idea of origin-destination matrix. Origin-destination matrix is not only the fact that we have an origin here of some trip and then a destination there. The idea is that I want to use the origin-destination matrix to understand how many people move from one area to another area of a city, each interval time, probably also modulating this. And so I want to use the OD matrix to understand the load of a system, when many people is moving the system. Then you have to introduce some traffic dynamics in a network, because you represent a city by a network, and some nonlinearity inside. Nonlinearity means you have to introduce at least the idea of interaction among vehicles, the same interaction that create congestion. And then, okay, there is still a problem from how people indeed move, because I will show you something, but in some sense, when people organize the mobility, at least in a city, there is still an energy. There is a travel time that seems to govern how the people organize the mobility. And this is something that I want to study more. So first of all, if you want to see if, for example, some data contains information about congestion formation, you have a possibility is look to the fundamental diagram. Try to find the fundamental diagram. So this is data from GPS in a vehicle. It is about a sample about 5% of population of vehicle in Bologna. So not too big, but not too small. Only vehicle, private car. So this is private car. And we have at least a precise, because it's GPS, so we know with a certain sample, spatial sample is not too big, it's an order of kilometer, but we know which is the starting point, the end point of each trip, and the average velocity. This is very precise because it's the GPS data. So we can compute the average velocity of this sample of data. And here you have, for example, this is the line for the empty city. This is center of Bologna. So we are considering just the historical center. So the fact that it's 16 kilometers is not something special, because if you drive a car in historical center, 16 kilometers is still a good velocity. You have a lot of stop and so on. But as you see, when you look to the, say, rush hour, there is only a change of the slope. So there is not something that really can say it is congested or not. Of course, you can take the ratio of this. The ratio of this is not so small because it's 10 over 16 over 10, so you are losing 60%. But there is really not a clear indication, and this is, in some sense, something that we observe in many cases, and we also observe in the TomTom approach to this problem, where the average velocity is the only observable that you can measure to see how the city is congested. Our observable seems not to be relevant. And this is, for example, you can check this. These are the same kind of data. We use a normalized variable. It is the travel time for each, for the distribution of a trip, normalized to the average value. And this is for the bigger city in Italy. The travel time is not the same. It's different for Rome, for example, and for Milano or for Torino. You have different mean travel time. So it means that, of course, Torino, for example, has a quite good, also Milano, public transportation means, so people use car in a different way with respect to Rome. But if you normalize this, and this is a log scale, you get the collapse of a car, at least for this kind of data. So it means that you have some universal behavior, which is exponential, and the only difference between the cities is just here, where, in some sense, you start to use the car, because, of course, you cannot have an exponential which arrives up to the origin, because you don't use the car for something that takes 5 minutes. This is completely stupid. You lose the time just for parking. So here, there is a time at which you decide to use the car, and this is the real difference between the city, just there. And then you have this exponential behavior. So this is something that in physics say, but this is the maximal entropy principle, because if you apply the idea of maximal entropy principle, let's say, okay, take the information entropy and just say, okay, which is the distribution which maximizes entropy with a constraint that you have a travel time that is fixed by your average travel time in data, and then you get the exponential distribution. What means? It means that we have understood no, because it means that in some sense, if you look to a stationary situation of a city, you get exponential. That means statistical physics working for an equilibrium state, but you don't know what happens if you perturb the system, because this is not a particle like a gas particle. And so this is an open question. When the system is out of equilibrium, what happened to this? But the exponential, in some sense, distribution is quite strong. In this sense, there was, and still there is a debate about, okay, exponential distribution is simpler, so we look to power law. Power law means that we are complex. But finally, power law in mobility is the result that we are not looking to a homogeneous system, we are looking to a system which has different scale, and if you move a particle in the different scale with different velocity, you have a random walk where you can have a jump that create the idea that is a power law, but it's not really a power law distribution. It's just the overlap of exponential distribution. I will be back on that. This is the data that we are using now. We have in Bologna this kind of data. We are trying to analyze, and we hope to understand and to use this data to have the first approach to the digital twin. So these data are anonymous data from mobile phone that the public company like Telecom takes in order to optimize the signal of the antenna in order to cover all the possible space. So any antenna is a signal that can be modulated, can be stronger or weaker. It depends on how many mobile phones are in the area. So they want to localize some mobile phone with GPS precision and going to follow them in order to distribute the power of this antenna. And in a parasite way, we have GPS data position from mobile device on individual trajectory. And we use this data, we analyze this data for Rimini, and we are trying now to analyze in Bologna, but still we have no results. So this just is an idea of the quality of the data you can have. So the spatial scale is 20 kilometers. And these are trajectories that are reconstructed using this mobile phone data. And what is the advantage with respect to the other data, the data we have from the black box? The advantage is that here we have all type of mobility. So the idea is that with black box, we see traffic. but we don't know what are doing people if they're not using the car. Here we have an idea of traffic and also of other type of mobility. So, okay, first of all, we try to get some measure of the representativity. And if you are looking to, this is data from a coil, the blue one, a coil of the system. And this is, okay, is an average data for the week. We are looking in August 2020. And here the dot line is how this GPS data is able to reconstruct the flow in a country road during a day. And okay, we have only a very small penetration, it's just 1.5%. But it seems that when you have a road where you have, this is a flow from an hour, so 1,000 vehicles per hour, then you have an idea of the traffic flow. So I have to go. So this is, for example, the length and the time distribution for what we observe in the trajectory. And the dot line is a power law interpolation. So you see that for the length, you can have a good power law interpolation starting not at the beginning, but after 1 kilometer and so on. For the activity duration, instead, the power law distribution is not so good. So why this happened? If you look to the mean velocity distribution for each trip, we compute the mean velocity. You have this kind of picture, and here you, in some sense, have the idea that this is not the velocity of a single transportation mean of a single typology of mobility, because here you have slow mobility. Probably here you have a mobility in the country road. This is the highway, and so the idea is that you can, you can try to reconstruct the flow, but more importantly, you can use the fuzzy C-mean clustering in order to classify this kind of mobility using different features, and the feature relate to sinuosity, speed, minimum speed, maximum speed, average speed, and so on. And the result is something that we are publishing now. It results that you really disaggregate the data, and you have more or less a bell-shape distribution for the average velocity, that is what you expect. And you can have, for example, for Rimini, the impact of a different class. So class 0, 1, 2, 3. 3 is clearly a class with 113 kilometers per hour, that is highway. And I have not put here but this is something that is crossing the area. I don't care. And the other 3 classes instead are the class of traffics from the countryside to the Rimini city, and then the traffic in Rimini and the slow mobility in Rimini, which is related to this, slow mobility is related to this. And if you see here, that is in some sense also interesting, the traffic and the slow mobility in the city are of the same amount. And this is good. In Bologna, it's much less. Rimini is a city where people use bike, because they have done a policy with a good bike road. They have built now a park near the beach that is completely out of traffic. So people use a lot of the bike inside. But we have a strong problem with people from the country road to the city, because there is no connection between the country and the city. The car and is the only means. The other means are related to the, say, to bus, but bus are very inconvenient from a time point of view. So this is the idea that you can have a problem here, and we have to improve this. Then, okay, just to prove what I'm saying, this is the structure of a city that you highlight with this system. So this is the cluster of slow mobility, where you have a lot of things a lot of road near the beach. Then this is the historical center, this is Riccione, this is Torre Pedrera, which is near Rimini, our things. So here you find the low scale traffic road. And then if you go to the other class, this is the class of urban traffic. The fact that we have this is just because we try to get a connect network, but these are the main road in the city where the traffic is allowed, so people is moving. Then you have the traffics. This is the country road which are connecting the country with Rimini, and this is Via Emilia. This is our important road for our coil was here. That is the most important here, and this is really what take the more traffic load in the Rimini. 40% of traffic are just using this kind of network, not the other. And of course, if you look to the light, this is the highway. So the last class is for the highway. And so, for example, coming back to the problem of how to explain exponential and power law distribution. So if you disaggregate the data, and then you normalize with average length and average travel time, the distribution, then you get that all the class, the free class, not the highway, will more or less collapse. And here you see that they collapse in a single exponential distribution. And this means that what we observe here in this slide about this distribution is just the fact that we take together three types of mobility, because we take together slow mobility in the center and mobility in the country road. And then you get the power law. Situation is not so simple because I skip here the picture, but now I can comment, because if you look, so for example, this is how a travel time, the average velocity increase with the travel time. And here you observe that as the trip become longer, the average velocity will increase. What means? Means that when a people is using car, it choose the road network as a function of how the distance that you have to cover. And then he organized the trip not in a simple way. It's not if he start in a network, remain the network. He can use different network, and this is complicated to understand how this is related to this, because this is not simple the overlap of free exponential distribution with this proportional. So if you take this proportional probability to get people in some network, and then I compute the overlap of free exponential distribution, I do not get the power law distribution. So it is more complicated, and this has to be studied. Then I have 5 minutes, I want to just say something about what simple model can teach us about congestion. So this is a quite simple model, very simplified. So you lose the road, you lose almost everything. You just represent the city with some area where people is moving from this to this and this to this and so on. You just move, for example, a quantum of people. So each of this coin is a quantum of people. And then, for example, you just choose to move just one coin. So it means that there is a finite flow capacity to move people in this system, just moving one of this. And then you can also introduce a maximal capacity. So if it's at the maximal capacity, when it's congested, that people cannot move here. So you have to expect that the congestion goes down. And then you have a Markov dynamic. So quite simple. You just choose this probability, and that's all. So you can formalize this. It's not difficult. But then you get two types of results. First result is that if you just take the transition probability matrix, transition probability rate, which is related to OD matrix, then you can say, okay, which is the stationary state? If a stationary state, and then you get a flow that is, and you get a flow that is in some sense fixed for each connection. You have a fixed flow for each connection. Then there is a solution for this equation, which is in some sense proportional just to the product of the components of a stationary vector times the number of coin or particle vehicle I have in each road. And then you realize that if this P is not constant, you create a congestion just in the area where P is maximal, because here you are concentrating the value. So this is a system where you can immediately understand that in the city there are regions where congestion appear. It depends on how many times you have this traffic load, but sooner or later congestion will be there. So in principle say, okay, but this is because city is not balanced. You have place where people is coming too many people, and then there is this concentration. So try to get a balanced case. Then it is possible to have a uniform distribution of people in your city, even if you are moving in a completely random way. No, you get exponential. So it means that most of a node will be empty, and then you get this exponential queue with nodes that are congested in any case. So it means that congestion will appear even if you have a stationary distribution without any problem in your system. It depends on the scale time. And you can also see what is the effect of a congested state if you have this congested state, and you can also prove, say, a dual effect that if you take the system and you compute the left eigenvector is related to the distribution of congested state in the system. You can just make a calculation. This is simple. So just take, for example, a very simple model that is a loop where you move up and down this coin, this particle with equal probability. This is completely stupid things. And then you introduce maximal capacity. What happened to this system? First of all, you realize immediately that this system is really not, each node is not a representative node of the system. So if you try to get the idea of Boltzmann that each particle represents of the gas, here no. There are some outliers that get an average number of particles. Theoretically is 5, and you get 8, 9. So you get particles that remain congested for a very long time. So it means that such kind of system, you have two types of evolution. Is one step, so you move one particle per time, or a synchronous evolution. All the node moves particles. But in any case, you get that the system is not relaxing really to a stationary state. But you can have a good approximation for each node with an exponential. So this is the probability distribution of the state of a node. And you see that is an exponential with a lot of time the node is empty, and but you have also time which the node becomes congested. And there is a difference between asynchronous and synchronous dynamics. You can see, first of all, this. When you have a synchronous dynamics, the number of empty nodes is much less. And you can understand this because if everybody is moving at the same time, the empty node will disappear faster. But then you see also that exponential is not so good to represent the system. And if you go with to understand, for example, okay, but it's possible to understand how for example, in this case, the empty node distribute in the system, because the idea that you have is that if congestion appears, it appears like a cluster. because you start with a congested road, when you congest the other road, and so on and so on. And here for the asynchronous dynamics, you just compute the probability to have an empty node if you are at state n. So your neighbor is empty and you have n particle, and here it's almost flat. Let's say that there is no correlation between the fact that you have n particle and the node, your neighbor who is empty. And if you take the synchronous dynamics, that is the real dynamic, because everybody is moving in the same time, then you have this is the power law, almost with some cutoff at the origin. And this means that the fact that the system do not spread the information immediately, so there is a lacking of time in which the information of the movement spread in the city, will create a force that is purely entropic, because it's a force that say the state of the system where the empty nodes are near are more favorite than the other. And this more is just like a power law. So it means that there is a longer range attraction. And we observe this in the system. So we have this. And if you take both finite capacity and the finite flow, you get that for the synchronous system in this simple case, you have a flat distribution. So here you get almost a uniform distribution in the system. And instead, for the synchronous dynamic, you get empty node from one part and congested node for the other. So you have a p-modal distribution in which you create congested node, even if there is nothing that creates congestion. It's just the fact that the dynamic of the system will get a solution which favors the fact that congested node and empty node are together. So this is an example, and when I skip the other that you can have, this is an example of what we are trying to do in Bologna. So I will go to the finite consideration about modeling urban mobility. So the idea is that to get a good model, we need data from Lagrangian point of view and data from OD point of view. So Lagrangian point of view will allow to understand how people really move, and if they use bike and if they use other kind of transportation means, and also how they build their path. Instead, the OD matrix is something that allows to estimate traffic load. Usually you have not enough data on individual level to estimate the traffic load. Then I still have a problem to study how the congestion appear in the system. There are recent papers that say congestion can be related to percolation. I don't know, but in some sense, if it's so, you have to prove in very simple system that really congestion can be explained with a clustering of some node, even if your system is in balance. There is no really concentration of particles. And then we don't know about applying control strategies. So what we do to avoid this, what are the main strategies? So I thank for your attention. And of course, I thank all my collaborators that are listed here, that are PhD students of laboratory. And this is my colleague, Nico Degisposti, which is an expert on dynamical system, which is working with me. Thank you for your attention.
Okay, so questions?
My question is regarding this Lagrangian approach that you mentioned that you use some data, but basically at the very end you use the final and the initial time and the final time, not the whole route, no?
We can also, okay. In this mobile phone data, we have also information on the route because we have a sampling every 5 seconds. So when the mobile phone is moving, we can reconstruct so we have this. Of course.
I have some. I mean, actually, in the question is that what you have in there is, especially when you have started to talk about the models before this one of the diffusion, you were talking about the different layers, no? So essentially the mobility categorized in three steps.
Sì.
And you were saying that the mix was not able to produce a power law. I mean, that's true. I mean, separate.
I mean that if I take the percentage that I see from the data of mobility in the free layer,
Yes.
and I just say, okay, I take a point, a vehicle and an individual which start in a layer and remain in the layer,
Yes.
then I do not reproduce.
No, that's right. But then the power law is coming from interaction
Yes.
between the different layers. Okay.
Yes.
Okay.
This
So
is
how
at
the
least
congestion passes from one to the other. Okay.
so it
that's
means that
interesting.
if you pass from one to the other, then you can create a
Okay.
power.
And then we will talk also about the part of the diffusion, because I know some results from computer science and congestion in computers systems that could be also translated to here. Okay. So any other question here? No. And online, because I have here the chat. No. Okay, so well, then let's thank Armando again.
There will be a question from him.
Will be here around. Anna, you have a question?
Let's say less technical. So which are the challenges that you can foresee about data sharing? Because I think that the main problem at the end will be like accessing like data, right? So which are the challenges that you can foresee? Because so what is happening is that Twitter is closing the API. So we'll see how the social media data, then mobile phone, yeah, that's okay, but usually they really cost a lot, so they are not affordable. So can you foresee any solution?
So I have no solution for that, but
Okay.
of course, okay, now in Italy something is happening, but I hope also in Europe. The idea is that a mobile company and also private insurance company and probably also the social media have to be forced to give the data to the university in order to make this study. So it's not correct that they collect data and that they will sell the data also to the public institution where our main purpose is research. We are not doing money with this stuff. So if you sell the data to a company for have an idea if you open a shop or a commercial center in the dark, that's okay. But I hope that the policy will make some rules in order that you can ask this data with all the anonymous procedure that you want, but you can have this data by free if you are a public institution. So this is, but up to now is not possible. And you are right, there are some open data. For example, Bologna has an open data policy, but it's only data that is collected as a municipality. There are no possibility to get the data from telecom. Even, okay, it's possible if you have a relationship, you can give an agreement, but they want to sell the data file.
Yeah, okay. Yeah, thank you.
Mando.